Last episode we grew up, we threw away the handwritten training loop and let nn.Module hold our parameters, while an optimizer, Adam, took the steps for us. But everything we trained was still secretly one straight line, one linear layer, one decision, a plane slicing the world in half. Today we find out what happens the moment you stack two of them, and we point it at real data that no straight line can ever split. Here's the thing about a single linear layer. It draws exactly one straight line. That's all it can do. Feed it the price and size of a house, it draws a line. Feed it anything, it draws a line. And the real world is almost never that polite. Real data curves, it loops, it wraps around itself. So a straight line, no matter how cleverly you place it, is going to get a lot of points on the wrong side. So the obvious move is stack more linear layers, right? 2 of them, 3 of them. But here's the cruel little secret of linear algebra. A linear layer feeding into another linear layer is just one bigger linear layer. 2 lines collapse back into one line. The math literally folds them together. To get a curve, you need to break the linearity between them. And the simplest break in the world is ReLU. If the number is negative, make it 0. Otherwise, leave it alone. That tiny kink, that one bend, is what lets the network draw curves. And nn.sequential is how we stack it. Like Lego, linear, then ReLU, then linear, then ReLU, then a final linear. Each block hands its output to the next. You read it top to bottom, and that's literally the order the data flows. No forward function to write, sequential writes it for you. Those middle layers are 32 wide. That number, the hidden dimension, is the width of the net's thinking. More neurons, more capacity to bend the boundary into complicated shapes. But it cuts both ways, too much width, and the net starts memorizing the noise instead of learning the shape. 32 is plenty for 2 crescents. The last layer outputs 2 numbers, 1 per class, not probabilities, just raw scores. We call them logits. The bigger logit wins, and cross-entropy loss is built to read exactly these. It takes the 2 raw scores and the true label and tells the net how wrong it was. In one number, it can push downhill. Under the hood, it runs a softmax to turn those scores into probabilities first, but the loss handles that for you. Before we train, we split the data, learn on one half, judge on the other half it has never seen. This is the honesty check. Any net can ace the questions it studied. The test set asks the questions it didn't. If it does well there, it actually learned the shape. And we track 2 things as it trains. Loss is the number we minimize, the thing the optimizer actually chases. Accuracy is the number we report to humans, the fraction it got right. Watch how they move. In the first dozen epochs, the loss falls off a cliff and accuracy shoots up, then both flatten out. That plateau isn't a bug. The crescents are noisy, they overlap a little, and some points genuinely sit on the wrong side no matter how you bend the boundary. So the net settles around 97% on what it studied. It learned the shape, it just can't unmix the noise. Behind the scenes, every epoch that boundary is bending, wrapping itself around the 2 crescents until it threads right between them. Okay, the whole thing, 2 pages, mlp.py, make the moons, build the stack, train it, score it. Nothing here you haven't met. It's the same nn.Module and Adam rhythm from last time, just deeper, and aimed at data that finally needs the depth. Up top, the imports and the data. Make moons from scikit-learn gives us 1000 points shaped like 2 interleaving crescents with a fair bit of noise. We pull out x and y, then train test split carves of 20% for testing, then the conversion every PyTorch project does. NumPy arrays become tensors, float for the features, long for the labels, because cross-entropy wants integer class indices. The model. This is the Lego tower, nn.Sequential, and inside it linear 2 to 32, ReLU linear 32 to 32, ReLU linear 32 to 2, 2 features in, 2 logics out, 2 ReLU kinks in the middle doing the bending. 1 line of code, a whole network. Loss and optimizer, cross entropy loss for the classification, and Adam over model dot parameters with a learning rate of 100th. Same 2 lines as last episode. They don't care that the model got deeper. That's the whole point of the toolkit. The loop. For each of 201 epochs, zero the gradients, run the data forward to get logits, compute the loss, call backward, step the optimizer. 5 lines, the grown-up loop you already know. The only new bit is right after. We compute accuracy by taking the argmax of the logits, comparing to the labels and averaging the hits. Every 10th epoch we print loss and accuracy, so we can watch it climb, then settle. And the verdict. We flip to a well mode, turn off gradients with no grad, run the held out test, set through once, take the argmax, compare to the true labels, and print the final test accuracy. That one number, about 0.96, is the honest grade. It lands just below the training accuracy, which is exactly what you want to see. The net learned the crescents, it didn't just memorize them. And there it is, a real neural net on real data scoring itself honestly. But notice what we did. We loaded the entire dataset into memory at once and fed it through in one giant batch. Fine for 1,000 points, useless for a dataset that's millions of rows or a stream of text that never ends. Next episode we fix that. Datasets, data loaders, and finally getting all of this off the CPU and onto a GPU.